This is assignment number 1, and for question number 1 we have to prove that A is equal to B. Both the matrices are equal. So for first we'll define, let us say A is equal to, let's say A1 B1 C1 D1, and let's consider B as A2 B2 C2 and D2. What we have to prove? We have to prove that A1 is A2, B1 is B2, C1 is C2 and D1 is D2. For that we can easily prove that A, if you take A of 10 as xy 10 as B into 10. So A into 10 will have the first column vector of that matrix A. That means A1 C1, that is equal to A2 C2. This implies that we have A1 is equal to A2 and C1 is equal to C2. And in similarly we can have A into 0 1, that is equal to B into 0 1. So for that we'll have the second column of the first matrix as well as second matrix B1 D1 is equal to B2 and D2. So from that we have B1 is equal to B2 and D1 is equal to D2. This implies that we have matrix A is equal to B. In question number 2, we have to check, we have to basically explain geometrically why we have this involuntary matrix satisfy A square is equal to identity. That means we have the self inverse of the matrix. We have 2 by 2 matrices. So let us consider one of the matrices, let's say 0 1 and 1 0. So what it means, if we take, suppose let's say xy, that means this matrix or this transformation will give xy as, it will give as y and x. What it means? It means, suppose if you consider x-axis, let's say this is 0 0, this is a 1 and 2, this is a 1 and 0, and this is 0 and 1. What will happen to all these points under this transformation? So basically 0 1 1 0 and let's say 1 0 will be transformed to 0 1. What it means? That means we have a reflection of all the or you can say the reflection about a line y is equal to x, which is basically passing through the origin. So we have these, basically we will have this reflection of points. That means this 0 1 will be reflect on this, and this will be reflect to this one. Or let's say the other matrix, that means this is basically a reflection about y is equal to x line, which is passing through 0. And what about this matrix 1 0 0 minus 1? What will happen to xy? This xy will be transferred to x minus y, and same goes for the let's say minus 1 0 0 minus 1, and then xy will be transferred to that is minus x minus y. So we have the line y is equal to minus x, this is also a line y is equal to x. So we have this. So that means the transformation, all these matrix based transformations or reflection. Reflection about about some lines to origin. In question number 3, we have to explain why we have this multiplication. If we have 1 and 0 0 minus 1 and minus 1 0 0 1, basically from the previous question we can have that uh, these matrices are some reflections, and when we multiply the reflection in the reverse order we basically have the same things. So this reflection basically is about y-axis. This is about the x-axis. This is about in the reverse manner, that means the x-axis, and then y-axis. So that means we have the reflection first with y-axis, then x-axis here, y-axis, or you can say x-axis, y-axis. Why? When we multiply with this vector, say xy and xy. So basically we come at the same point. So both are equal. In question number 4, we have to prove that three conditions. Any straight line is basically straight line under the image which of the matrix which is invertible matrix. So that means we have this A inverse exists. If A inverse exists, so let us try to consider any straight line. That means ax plus by is equal to c. So we can write out this in the matrix form. Let's say AB and then xy is equal to c. So that means A inverse exists. That means A inverse is basically identity. So we can write down this AB xy is equal to c. That means identity. So we can replace here AB, and then can basically write down inverse A into xy. We have to show that this is also a straight line. To prove that if we start with the straight line, we get the straight line. So if A inverse is invertible, that means A inverse will have some entries. That means let's say you can say A1, A2, B1, B2. Now A and B and then matrix A inverse, will count this, will have some A1, A2, B1, B2, which is nothing but some, you can say D1, D2, D1, D2. So this is D1, D2. So you can have D1, D2 and then matrix and then xy, which is also a straight line. So for any straight line is a straight line, any straight line passing through, that means so B, any straight line passing through origin, that means C is equal to 0. In this straight line we have C is equal to 0. Any two parallel straight lines are basically parallel straight line, that means for the same value of AB we have to consider two, C1 and C2. In question number 5, we have to prove that for a nilpotent matrix, that means e to the power m is equal to 0. So we have a nilpotent matrix, m is equal to 0. That means A has the potential to be a null matrix. M is greater than equal to 1. We have to show that I plus A is invertible. That means there is this matrix B such that this is equal to identity, or you can say that B into I plus A, which is also identity, because for inverse, that means for A matrix A said to be invertible if there exists and matrix B such that A is equal to identity or B is equal to identity. So we need to find out matrix B, and for that we have to basically consider, if we take B is equal to, let's say, identity, and we have to construct a B in such a that I plus A multiply with it is basically an identity matrix, and we have to consider also that is a nilpotent matrix. So if you consider I minus A plus A square like that up to a to the power m minus 1 and plus a to the power m, which is basically equal to 0, not equal to 0, and this term is basically 0 because of a to the power m is equal to 0. That means if you consider B as, you can say, minus 1 to the power, say, I, a to the power I is from 0 to m minus 1. If we multiply this B here, we will get identity. So that means we have a a matrix B which gives us identity by multiply with I plus A. That means I plus A is invertible. In question number 6, we have a relation that A transpose, if it is a transpose 0, then we have this A is nothing but a null matrix. Why? If we take the trace of both sides, we take trace of both sides, A transpose, a trace of 0, that means we have this trace is basically summation of Aij square, and and this is equal to 0. If it is true, that means sum of all the elements basically 0. That means Aij 0 for all ij. That means all the entries are 0. That means A is a null matrix. But this is not true if A is complex. This is true when A is real. A is real, that means all the entries are real numbers. If we consider let's say some matrix which is not real, that means a complex matrix, let's say 1 or iota 0 0, and if we take A transpose, which will be a null matrix, but A is not a 0 matrix, that means this result is not hold for complex matrix, but this result holds if we have a conjugate and transpose. That is means A conjugate is equal to 0, then we have this A is null matrix. Why? If we take trace of both side, A conjugate, that is 0, so that means we will have this absolute value of Aij is equal to 0. That means all the basic terms are 0 for all I and j. This means A is equal to 0. That means A is a null matrix. In question number 7, we need to find out the determinant of this matrix by using the permutation involving S3. S3, that means we have the permutation on elements 1, 2, 3. So in general, the determinant of any matrix n by n is given by summation, where the permutation basically belongs to Sn, and then we have this sign of basically sigma, that is positive or negative. That means this sigma can be written as if even number of transposition, even permutation. If it is odd, product of transposition, that means odd permutation, into A1 into image of that number A2 sigma of 2 up to An sigma of n. A of sigma, that means suppose we have this sigma, let's say 1 2 3 4, that means sigma of 1 is 3, sigma of 2 is as 4. So in S3 that means for this matrix we have, that means 3 by 3, A11, A12, A13, A21, A22, A23, A31, A32, A33. So determinant of this matrix A is basically summation of sigma, which is in S3, and then we have this sign of all the sigmas, and then we have A into 1, sigma of 1, A of 2, sigma of 2, A of 3, sigma of 3. So we'll have S3 as the first one is the identity. Identity means that means 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. That means sigma of 1 is 1, sigma of 2 is 2, sigma of 3 is 3. Same thing goes with other elements. That means we have to in Sn we have factorial n elements. In S3, so it will be factorial 3. Factorial 3, that means 6. There will be 6 elements. So we have 1, 2, 3 mapped to 3, and then we have 1, 2, 3. 1, 2, 3. 1 is mapped to, or you can say 1 is mapped to 3, and or we can write down that 1, 3, 2 is mapped to 2, and the other one we can write down that 2, 3. 2, 3, 1 is mapped to 1, or we can say 3, 2, or 3, 2, 3, 2, 1, 3, 3, 2, 3. Okay, we have write down this one, and then we have 1 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 1, and then 1 is mapped to 3, and 2 mapped to 1. 1, 2, 3, 4, 5, 6, all these elements. So we can write down this as first one I, that is the identity, that means the even permutation, it is always even, so that means +1, and then we have A1 sigma 1 is 1, A2 sigma 2 is 2, A3 sigma 3 is 3, plus for this, that means A sigma of 3 is mapped to 3, sigma 1 mapped to 2, sigma 2 mapped to 1, and this is odd permutation, so minus A1 sigma of 1 is 2, A2 sigma 2 is mapped to 1, A of sigma 3 is mapped to 3, minus for this, that means sigma 2 is mapped to 2, sigma 1 is mapped to 3, sigma 3 is mapped to 1, because for this we have, that means sigma of 1 is 3, sigma 3 is 1, sigma 2 is 2. So minus we have A1 is mapped to 3, A2 is mapped to 2, and A3 is mapped to 1, and minus A1 is for this 1 mapped to 1, and then K, and then 1 A1 1, A2 3, A3 2. For this is even permutation, we can write down this as the transposition of 2, so plus A1 2, A2 3, A3 1, and for the last one we have a13, a21, a32. So just put all the value. For example, a11 is 1, a12 is 2, a13 is 4. When we put all these value, the answer we got 28.